All right, we are talking about the setup for the lesson 0.1.7 lab. And the introduction to this lab talks about how when we burn things like we've been doing in class, there are consequences. For example, we're seeing a change in the frozen areas at the north and south poles of the Earth, the melting polar ice caps. You may have seen some of the sad pictures of the polar bears stranded. So we're going to be talking more about that as the year goes on. So, for this activity, it asks you to warm up by thinking about things that produce energy versus things that require energy. So, in class, some people brainstormed things that produce energy would be things like burning fuel, like we've been doing in class. The sun burns or produces energy. Things that require energy would be cooking, maybe boiling water. Melting is a process that requires energy, which is kind of giving away the answer to number two here. We talked about, is this statement true or false? It takes no energy to melt ice that's at 0 degrees Celsius because it is already at its melting point. That's false. When you go from 0 degrees Celsius solid to 0 degrees Celsius liquid, that process requires energy. It takes energy to move these particles further apart from each other, and they start moving faster as they gain more energy. So going from a solid to a liquid definitely requires energy. What would happen if you placed a piece of ice in a glass of room temperature water? What will happen to the temperature of the water? Well, it will decrease because the ice cube is colder than the room temperature water. So as it melts, there's going to be a transfer of energy from the water to the ice cube, and so the resulting temperature of both the melted ice cube and the original water is going to be a lower temperature. What I asked everybody to do for this was to design a procedure, design a way that you can actually figure out how much energy is required to melt an ice cube, how much energy per gram of the ice cube. So everyone in class is going to get an ice cube that's at 0 degrees Celsius, and you need to figure out how you're going to measure some different things and ultimately calculate this energy required to melt the ice cube. So in class, people brainstormed things like they're going to measure the temperature of the water before the ice cube melts and after it melts. They also said we're going to need the mass of the water before you put the ice cube in and after, because we're going to need to know the mass of the ice cube. And we're going to be using styrofoam cups. We're going to be using thermometers, probably the temperature probes, and water and scales. So once that was checked off, people were writing out their procedure, and from what I could see, they had things like step 1, 0 styrofoam cup on the scale. Step 2, add 100 grams of warm water. Step 3, measure and record the temperature of the water. Add ice cube. After melted, record final temperature of the water and its mass. And then different groups did different things for their data table because it was really up to them for setting this up. I did the mass of the ice cube in grams, the initial temperature of the water in degrees Celsius, the final temperature of the water, degrees Celsius, and the mass of the water at the start. And then I did trial number 1, trial number 2, and included a spot for the average. So I'm going to sketch this out. I'm not being super, oops, this is definitely not enough space. Okay, I hope I can write small enough in here. So when I collected data for the first experiment, I found that the water started at 40.4 degrees Celsius. The ice cube was 5.49 grams. I measured out 98.48 grams of water. And after the ice cube melted, the final temperature of the water was 34.3. Trial 2, the ice cube was a little bit bigger, 6.96. The initial temperature of the water was 44.7. The final temperature of the water was 35.9. And the mass of the water was 98.36. So for the average here, my average mass of the ice cube was, 6.23. Initial temperature of the water on average was 42.55. Final temperature of the water on average was 35.1. And the mass of the water was 98.42. So on average, the temperature change was 7.45 degrees Celsius. So now I can use what I've learned in my experiment to do some calculations here. So just to do a little sketch, here's my cup, here's my ice cube. The energy released by the warm water to the ice cube is the same as the energy absorbed by the ice cube in order to melt. So if we figure out the quantity of heat released by the water, we're going to know how much energy was absorbed by the ice cube. So let's review our formula. Mass of the water multiplied by the specific heat for water, which is 4.2 joules required to heat 1 gram, 1 degrees Celsius, multiplied by the change in temperature of the water, will let us know how much energy. So the mass of the water on average was 98.42 grams times by 4.2 joules over grams degrees Celsius multiplied by that change in temperature, which for my data was 7.45 degrees Celsius. Punch that into my calculator and I get 3,079.6 joules. That's how much energy was released by the water, which again, we're going to make the assumption that this is the same as the energy absorbed, by the ice cube. We're not done because we need to know relative to how big the ice cube was, how much energy it took. So we want joules per gram, or it says kilojoules per gram. So looking back at my data, on average, my ice cube was 6.23 grams. So that's 494 joules per gram. That's the same as 0.494 kilojoules per gram. Okay, cool. And in case you're curious, we've been doing these calculations in joules, but we could go back and figure this out in calories. It's the same thing. Mass of the water, 98.42. The specific heat in calories is 1 calorie per gram degrees Celsius multiplied by the change in temperature. So if I punch this into my calculator, it's going to be a smaller number because it's in calories instead of joules, but same amount of energy, just using a different unit. It's one of the annoying things about science. So instead of 3,000 something, this is 733 calories. That's how much energy is required to melt that ice cube. Okay, cool. Let's take a look at some of these follow-up questions. For the making sense question, it says, draw a representation of the investigation you performed and label where the energy was involved. Identify any conversions and transfers. Well, this is going to be one of our simpler drawings. There's energy, I should specify it, thermal energy from the water is transferred to the ice cube. There's some new terms here. Exothermic processes are processes to which heat is transferred to the environment. Endothermic processes are processes in which heat is transferred from the environment. In general, if you are in the surroundings, an exothermic reaction or process will feel warm to you, and an endothermic process will feel cold to you. Is the process that you completed in the lab today exothermic or endothermic? You can think about it this way. If you touched an ice cube, would it feel cold to you or would it feel hot to you? And the answer is it would feel cold to you because heat is transferred from the environment. In our lab, it was the warm water to the ice. And by heat, I'm going to change this. I'm going to say thermal energy. Got to get my terms down. Thermal energy. All right. Then there's a little equation. We always do the final temperature minus the initial temperature. So in the lab today, would this number be positive or negative? Well, it got colder. So it's going to be a small number minus a bigger number because the starting temperature was warmer. So we would get a negative. Show our work or explain. I'm just going to say the final temp was cooler. When a process is exothermic, remember this is when the surroundings get warmer, will the change in temperature of the surroundings be positive or negative? Explain why in terms of transfer. In this case, it would be positive because in an exothermic process, the surroundings get warmer. I should say the surroundings gain energy. Energy is being transferred to the surroundings. And then it's the opposite for this one. When a process is endothermic, the change in temperature will be negative, just like we saw in today's lab. Because in an endothermic process, the surroundings get cooler. The surroundings transfer away energy. Transfer energy away. Okay. There we go. All right. Let's take a look at the homework for this lesson. First one, if you consider a combustion reaction to be your system, would you call this reaction endothermic or exothermic? Explain. Well, in combustion reactions, heat is being released. Think about fire. It feels warm to you. So exothermic, because combustion reactions release energy. Consider the following scenarios. Draw a representation showing the energy transfer happening. First, there's an ice cube melting on the countertop. So draw a little water there. Energy from the counter is being transferred to the ice cube, and energy from the air. How about an ice cube tray? It says, filled with room temperature water, placed in the freezer. In this situation, energy is being transferred away from the ice cubes because the freezer temperature is cooler. Number 3, a chemical reaction between substances A and B occurs in a beaker. When the beaker is placed in a small pool of water, the water that comes in contact with the beaker freezes. List at least one object that's part of the system. Well, the system would be the chemicals here. So I'm going to say chemical A is one object. What are some objects that are part of the surroundings? Well, the beaker, because it's holding the chemicals, the water. I could also say the air. In the diagram above, show the direction of energy flow. Well, if the water is freezing, that means that energy must be going away from it. So this reaction must be endothermic and absorbing energy from the surroundings. If you were to touch that beaker, it would feel cold. Again, because energy is being transferred to chemicals A and B. So this is an endothermic reaction because it absorbs energy from the surroundings. All right, and the last part of this lesson is some Unit 0 review. So let's keep going here and get these taken care of too. Number 1, you fill an empty ice tray with water and place it into the freezer. Ice forms because, why? Energy is transferred away from the water, that's true. Causing water molecules to speed up, no. If they're having energy transferred away, they're going to slow down. So let's look at B. Energy is transferred away from the water, causing water molecules to slow down. Yes. And then let's just look at C and D. C says energy is being transferred to the water. That's not true. It's in the freezer. So the freezer temperature is going to be cooler than the water that you just put in there. So C and D don't make sense for that reason. Number 2, coal, a fossil fuel, is burned in the process of generating electricity by converting chemical energy to thermal energy and then the transfer of energy to water. Which of these statements is true about the use of coal to produce electricity? Once a sample of coal is burned, more can be produced from the same materials in less than a year. No, because coal is a fossil fuel. Letter B. Once a sample of coal is burned, the energy that was transferred to the atmosphere during combustion is gone. Well, it's not gone, it's just moved somewhere else. Letter C. Once a sample of coal is burned, the chemical energy released during combustion is available for transportation in the future. Well, if we think about what we know about this, the combustion products are carbon dioxide and water. And at this point, we haven't gotten to a place where we can easily turn water into hydrogen gas and run the car on hydrogen gas. So, I mean, I hope this becomes true someday, but at this point, I'm going to have to say that D makes the most sense. Once a sample of coal is burned, the effects of that combustion reaction may be felt for many years into the future. Because, as you probably know, there's a lot more carbon dioxide in the air right now than there used to be. All right. Number 3. Equal masses of water and iron metal are both heated with 200 joules of heat energy. Which one has the greatest temperature change? Well, water takes 4.18 joules to heat up 1 gram of it 1 degree Celsius. Iron only takes 0.45 joules to heat up 1 gram by 1 degree Celsius. So the iron is going to have the greatest temperature change, because with iron takes less energy to change the temperature of it than it does to change the temp of water. All right, number 4. Which mass of water required more energy to change its temperature by the amount specified? Explain your reasoning. Okay, 100 grams of water from 20 to 60, that's a change of 40 degrees Celsius. In letter B, you're changing 200 grams of water, but only by 25 degrees Celsius. So I think it's going to take more energy to do letter B, but let's just prove this with math. So how much energy, Q is the quantity of energy, does it take? So I need to do mass, 100 grams, times the specific heat for water. I'm going to do the 4.2 joules per gram degree Celsius, times the change in temperature is 40 degrees Celsius. This comes out to be 21,000 joules. Okay, how about letter B? Q is 200 grams times 4.2 joules per gram degree Celsius times a temperature change of 25 degrees. That's 16,000. Oops, I wrote this wrong up here. Sorry, I was looking at my wrong answer. Go back. Sorry, letter A, if you punched that in, you were probably really confused, is 16,800, and this one is 21,000 joules. So letter B requires more energy, just like I predicted, because it's twice as much water. All right, let's see what we've got going on next. Oof, this looks like a big table. Okay, I'm going to give myself some more space here for this calculation, like the whole page, because this looks long. All right, let's do this. Let's get this done. Sometimes the big and scary ones aren't as bad. Turn out to be the easy ones once in a while. All right, it says methane and propane are both gases that people burn for energy to produce light and provide fuel. 2 students conducted an investigation to determine whether more energy was produced from the combustion of methane or from the combustion of propane. The data they collected is shown here. In each case, they heated 150 grams of water. Okay, so for methane, it looks like they burned off, I'm going to subtract these really quick, 10.58 minus 10.34 is 0.24, and the temperature changed by 18.54. In the second trial, they burned off 0.37 grams, and the temperature change was 17.86. And that was everything for methane. So I'm going to write the averages over here. 0.24 plus 0.37 divided by 2 is 0.305. And over here, 18.54 plus 17.86 divided by 2 is 18.2 degrees Celsius. Okay, so these are going to be my averages here. I'm going to circle these like twice. All right, how about propane? They burned off in this one, punch this into my calculator, they burned off 0.28 grams, and the temperature went up 18.15. And for propane trial 2, they burned off 0.57, and I'm subtracting these. The temperature changed by, wow, a lot more, 36.37. So I'm going to find these averages by adding up these two and dividing by 2. This one comes out to be 0.425. Circle that one a few times. And the temperature change on average, 18.15 plus 36.37 divided by 2 is 27.26. All right. Let's figure out how much energy was released for both of these in kilojoules per gram. All right, I'm going to sketch a little picture of what we've got going on here. We've got a can with 150 grams of water in it, and we're burning methane first underneath this can. So I'm going to figure out the quantity of heat energy gained by the water. So I need to know the mass of the water, and I need to multiply that. It says it wants it in kilojoules per gram, so I'm going to use the joules number. 4.2 joules heat up 1 gram 1 degrees Celsius, and change in temperature. So now I can plug in my numbers here. The mass of the water was 150 grams times by 4.2 joules per gram degrees Celsius times by methane changed temperature on average from my chart above, 18.2 degrees Celsius. So when I plug that into my calculator, 11,466 joules of energy were released. Now, to get that into kilojoules, I'm going to divide by 1,000. That's 11.466 kilojoules. Now, I want to know relative to how many grams of that fuel burned off, how much energy this is releasing. Because if I burned it for a really long time and that's all the energy I got, that's not very efficient. So I'm looking at my methane, and on average I burned 0.305 grams. Again, if you're wondering where is she getting these numbers, these are just from my chart, these numbers that I double circled. So right now we're working on methane. So when I take 11.466 divide by 0.305, I get 37.6 kilojoules per gram. That's how much energy was released per gram burned by methanol. All right, let's do the propane. So for propane, same thing. We're going to figure out the quantity of heat. So we need the mass of the water. It said it was always 150 grams times by 4.2 joules per gram degrees Celsius times by the change in temperature for this one was 27.26 degrees Celsius. When I punch that into my calculator, it comes out to be 17,174 joules. If I divide that by 1,000, I get that into kilojoules, 17.174. Now I want to divide by how many grams of propane actually burned on average. So divide by 0.425 grams. My final answer here is 40.4 kilojoules per gram. That was for propane. Alright, so explain what you can conclude based on this data. Propane releases more energy per gram. You could also say propane has more potential energy per gram. Identify at least 2 questions that you have about these data. So this I'm going to let you do. So one thing I noticed was with propane, why is there such a big difference between trial 1 and trial 2, the temperature change? Like, did they forget? Because one, the temperature changed by 18, and the other one, the temperature changed by 36. And so my question would be, what was the burn time for this data? And then number 6, draw a representation of the experiment and illustrate to show how energy is involved. And we've done this quite a few times already, so hopefully you're getting a little more confident with these diagrams. So again, I'm going to show my can of water with my fuel burning underneath it. And I'm going to show a transformation that chemical potential energy is transformed into 2 things: thermal energy and radiation, light. And then for my thermal energy here, I'm going to draw some arrows from the flame to the water, some arrows showing energy being transferred to the air, and then some to the can. So I'm going to say thermal energy is transferred to the can, the water, and the air. We are in the home stretch. Last couple questions here. Number 6, if you take a 5-minute shower, you use about 100,000 milliliters, 25 gallons, of water. The water needs to be heated from 20 degrees Celsius to 40 degrees Celsius. How many calories do you need? Notice it's not joules. To warm the water for your shower. Note, 1 milliliter of water weighs 1 gram, and it takes 1 calorie to increase the temperature of 1 gram of water by 1 degree Celsius. Okay, so first of all, how many grams of water do I have if I have 100,000 milliliters? 1 milliliter weighs 1 gram. So I've got 100,000 grams of water that I'm trying to heat up for my shower. I recognize this as a heat equals mass of the water times the specific heat times the change in temperature type of problem. So the mass of the water is 100,000 grams. It takes 1 calorie to heat up 1 gram, 1 degree Celsius. And this is going up 20 degrees Celsius because it's going from 20 to 40. Punch that into my calculator. It takes 2 million calories to heat up my water. Then there's a follow-up question. How many grams of wood would you need to burn to take a 5-minute shower? Wood releases 4,000 calories per gram when you heat it. So I need 2 million calories of energy and wood releases 400 calories for every gram of it. So I'm going to divide. I need 500 grams of wood. It'd be interesting to convert that into pounds. Let me see if I can do that real quick, just out of curiosity. Grams. I gotta look up the conversion. Grams to pounds. 1 gram is 0.0022 pounds. So if we do 500 times 0.0022, try this again, 0.0022 times 500. Sorry, I was having calculator issues. 1.1 pounds. I feel like this is not an accurate problem because that's like not very much wood, and I feel like it would take way more. So that's okay. It's a pilot curriculum. Number 7. Last question. Woohoo! Which cup of water gets hotter? Explain your reasoning. If 450 calories is transferred to 100 grams of water that starts at 25 degrees Celsius, what about that versus 600 calories transferred to 200 grams of water starting at the same temperature? Well, right away I think letter A, and I think because it's only half as much water and it's not twice as many calories. So for this one, I think it would take 900 calories to heat up the double the amount of water to the same temperature. We can also use some math to prove this. So let's just back up our answer with math, even though it doesn't say we have to. 450 calories is the Q. So if I set this up, mass of the water times the specific heat in calories is 1 calorie per gram degrees Celsius, and I want to figure out how much the temperature is going to change by. I can divide both sides by 100 times 1, and I get 450 divided by 100. The change in temperature, this all cancels out, equals 4.5 degrees Celsius. So it's going to go up from 25 to 29.5 degrees Celsius in situation A. So let's try this again, but 600 calories equals the mass, which is 200 grams in the second one, multiplied by 1 calorie per gram degrees Celsius, multiplied by the change in temperature. Again, I'm going to divide both sides by 200 times 1 to get the change in temperature by itself, and the change in temperature for this one is 3 degrees. So 25 plus 3, it's only going to go up to 28 degrees Celsius. So my reasoning was correct that that top one is going to heat up a little bit more. So there you go. It was a beast